what version I got? It's the official UofM version, whatever it is. They push it out.
I just know that other Zoom meetings, sometimes something's gone weird and someone would have to pop out and then come back in and then it would be okay.
Yeah, it's kind of like reboot.
Apparently we're getting some space weather coming in. Only level G1, considered minor and above 60 degrees latitude, but I just got notice from Swipsy, so it's probably those flares I've been looking at all afternoon.
That's what I was just going to say, Jeff.
They finally got here. Okay. It is 7:30 and I'm going to switch to the meeting content. Joy, make it back?
Okay, Joy's coming back.
Any volume now?
There you go.
Oh, wow. Yeah.
Definitely. Well, sounds good. Can't see you, but it sounds good.
So we can hear you, but now you're invisible.
Is it too loud?
No.
Should I turn it down?
Okay, we can see you now.
Yeah.
That was a hard volume to find.
Yeah, I'm not even going to make
Windows jokes.
I won't even make Windows jokes.
I can do minutes. Yeah.
Thank you, Joy.
We could read your lips. But you know how we are. All you had to do was twitch, and we could take that as a volunteer, you know.
Yeah.
So,
and thank you. And I usually start about 7:35, John, just so you know. There's always a few people get in a little bit late. I think we call that UofM time.
What is the title of this?
Let's see. It is...
I was waiting for John to come in. It is, hang on a second. It's long, so I'm going to read it.
Oh, then if you could just put it in the chat, that would be great.
Okay.
Well, the title I gave you and the title that I might show on my first slide might not necessarily agree, but...
That's what's in the YouTube channel. How's that? Telescope Interferometry, Stars and Exoplanets.
Oh, you were the name of it.
Yeah, I was the name of it.
Yeah, she said it. She's okay. Okay.
Yeah, I'm so appreciative because I dropped it off this morning. Which morning isn't bad.
They've hijacked our meeting.
Right.
I'm talking about orange juice.
Yeah,
Okay, I'll pass that along.
Thank you.
We did make John a co-host, Jeff. I mean, a host. Yeah.
Yep.
Host.
Yep.
Okay, cool.
Got John, you, and Doug. Anybody else want to co-host? Just to watch for interlopers?
Probably me, and I don't think Adrian's going to be able to join us.
Yeah. Well, I figure Doug knows what he's doing, and you know what you're doing, and then our presenter. We should be covered.
Yep.
And myself.
Yeah.
That's the usual suspects, anyway. Where is Adrian today? Up north someplace? I don't remember.
Well, that's what you would think, because he goes up there a lot, but I don't remember exactly now.
Yeah, wherever it is, it's at least 50 miles away. So.
Yeah.
I shudder to think how many miles he's got on that truck, so, or car, or whatever.
Yeah, no kidding. Well, okay. I think we're close enough to 7:35. In fact, I believe we're almost there. So with that, welcome everybody. You'll find your way into the University Lowbrow Astronomers monthly meeting, the September edition. I'm sorry, what'd you say, Jeff?
Whoa.
Oh, that was pretty good. It is scary sometimes, isn't it? Anyway, we're a little group of, what Doug will tell us later, lasted 160 some astronomy enthusiasts. And just as a reminder, we are recording this on YouTube. So as tradition would have it, we always have our guest speaker first. That way, if some people were just interested in the guest speaker and did not want to stick around for our engaging and enlightening business meeting afterwards, it would give them the opportunity to escape after questions. So with that, our guest speaker tonight is Dr. Monnier, who has earned his Bachelor of Science from Purdue University, and he earned his PhD from the University of California, Berkeley. He's also a fellow at Harvard-Smithsonian Center for Astrophysics and an at-large member of the European Southern Observatory Scientific Technical Committee. Currently, we're privileged to have him right here at the University of Michigan. John is an expert in optical infrared interferometry and is the instrumentalist responsible for MERC, which is the Michigan Infrared Combiner, a beam combiner that allows all 6 of the telescopes at Georgia State University's Chara array to work together. He is interested in the direct detection of exoplanets and in studying how planets form in circumstellar disk. To do this, he plans to use not only his Chara technologies, but also Magellan adaptive optics to measure disk around young stars, and the ALMA radio interferometer to image the outer disk with high resolution. John's group was the first to combine 4 or more telescopes in the infrared part of the spectrum. This allows them to move from simple modeling of astronomical sources to reconstructing actual high precision images with milli-arcsecond resolution. They were the first to image the surfaces of main sequence stars other than the sun, including rapid rotators and very close binaries. John is now using this technology to study magnetically active stars to test theories of stellar dynamo and magnetism. On that note, the title of John's presentation is Infrared Interferometry at the University of Michigan, Imaging Surface of Stars in Their Nearby Environments. So with that, let's please welcome John Monnier. And the floor is yours, John.
Thank you. What time frame or should I be aiming for?
You don't have one. You can take as long as you want.
Okay. Wow. What is a typical amount? Are we aiming? It's more like half
45 minutes sometimes.
45? Okay.
Yeah, okay. Sometimes we've had people.
Okay, that'll be good.
We don't complain.
Okay, great. All right, let me share then. All right, can you see my slides okay?
Got it.
Yes, we do.
All right, so yeah, I'm privileged to give a kind of overview of work in my group and my collaborators at the University of Michigan, focusing on our work on imaging the surfaces of stars other than the sun. And I think that this group here will probably be particularly interested because a lot of the sources that I'm going to be showing today are well-known astronomical objects to naked eye astronomers or to amateur astronomers. You know, they're famous, bright stars, interacting binaries, eclipsing binaries, a lot of, again, I think you'll see some of your friends here. And if you have any questions as we go along, feel free to, ask, or I don't know if somebody's monitoring the chat, they could bring forward any chat questions since I probably can't see it at the same time that easily.
Okay.
All right, so I guess let's start up here. So just some reminders of why it's hard to image stars, and that is, the ability to, zoom up on an object, right, is related to telescope. And that's, of course, if you can even correct for, which is another detail. But under best case conditions, if you have adaptive optics, you can reach an angular resolution that's proportional to your wavelength over your diameter. So you want to go to short wavelengths, right? If you want good resolution, like in the visible, and you want to have big telescopes. And if you were to plug in the numbers for the biggest telescopes we have right now, We have, for instance, the Hubble Space Telescope, which actually isn't a very big telescope, but it is in space, and so it really doesn't have the atmospheric problems. And you can get approximately 40 milliarc seconds, or a 20th, about a 50th of an arc, a 25th of an arc second. I'm sure you are familiar with arc seconds and arc minutes, and so you can appreciate that the Hubble Space Telescope can give you image quality, surely smaller than a pixel in most cameras on average telescopes. The Keck Observatory can do a little bit better because it's 10 meters across, although it doesn't operate that short a wavelength in the diffraction limit. So say 30 milliarc seconds. And in the near future, we're going to have the EELT, the European Extremely Large Telescope, which is being built in Chile. And it will be a 39-meter telescope and reach down to even below 10 milliarc seconds. Now, that's great and all, but, is that good enough to look at stars, right? Stars are far away from us. So let's look at a graph here of how big stars are in angular size. And this shows all the nearby stars. On the left axis is how bright they are in the infrared, so the H magnitude, which, is very, of course, has the same basic scale as the, V magnitude that you're used to for stars. It's just shifted to the infrared. And on the bottom axis is how big the star is. So I mentioned that, again, the size of your telescope, you get better resolution. So at the top, you see a graph that shows the size telescope or interferometer that you would need to resolve these stars. So if we look at the current to even the ELT, you see that if you look at the color dots, you see there's a bunch of red dots in this circle. What that means is the only stars that you can resolve with these current telescopes are red giant stars, right? So, Albert Michelson resolved Betelgeuse and Antares and a few other objects back in almost exactly 100 years ago now using the 2.4 meter 100 inch at Mount Wilson. But even with the 10 meter class telescopes and even with the 39 meter class telescopes, you can see that really all you can see are nearby red giants, which are interesting. They have spots and they have mass loss, and you probably followed the dimming of Betelgeuse, right? That from last year. So there's definitely interest in looking at these objects, but certainly if you wanted to look at a broader range of stars, you need a bigger telescope. So the next sort of big telescope, the next facility that can do better is the VLT interferometer. Now, I'll talk more about interferometry a little bit, but basically the idea of an interferometer is if you can't make a telescope bigger, you can separate individual telescopes. And it's as if those telescopes are part of a larger mirror. And so if you reflect the light to a focus and you maintain the path differences just as you would if it were a large telescope, you can interfere the light coherently and recover information about these long baselines or the highest diffraction limited resolution. So the VLTI has baselines up to around 100 meters, which means it can do 10 times better resolution than, say, the Keck telescope. And you can see there with the VLTI, there's many more objects that you can do. Still mostly red giants, those red dots, but you can get down to some solar-type stars. You can look at Alpha Centauri, for instance. The Centauri, for instance, is large enough that you can measure it with the VLTI. But now with Chara, we can go another factor of 3. And also we can go even better. We can go into the visible, which gives us even more of a boost compared to the VLTI, which only is in the infrared. And so you can see here, we really are starting to sample all main sequence stars and subgiants and giants. Not every star, of course, but anything you can see, all these, what you might call infrared naked eye stars, these are all you see around 4th to 6th magnitude, you could resolve them, measure their sizes with today's facilities. And so the reason that I'm so lucky to is that the Chara array, which I'll say more about in a second, is the first interferometer to have the combination of angular resolution and sensitivity to measure all these different types of stars. So just a few words about my wonderful collaboration with Chara. So Chara is on Mount Wilson, California. If you're ever in LA, you should take, you've probably been to the planetarium there in LA. But if you want to go up to Mount Wilson, right, which is only about 45 minutes from Pasadena, you can see not only the 100-inch and the 60-inch and the solar towers, but you can see the Chara Interferometer telescopes and go to the small visitor center there and learn about some history as well as the new work going on Mount Wilson. It was funded by National Science Foundation and also the state of Georgia, which uses some funds of its lottery money to pay for educational initiatives, and some of that money actually pays the sort of the bills, the electricity and water bills for the observatory. There's, in addition to them, they also collaborate with other groups like us in Michigan, as well as groups in Paris and Grenoble and Nice and Sydney to build instrumentation for it. So basically the Chara and the Georgia State folks run the observatory, kind of like imagine a telescope, while other groups can also contribute instruments that then everyone can use. And indeed, Chara offers a couple months of observing nights to the community through the national lab, the national observatory groups, so that it's open to the whole U.S. community who want to use it. And with this, as I mentioned, we have the largest baselines in the world for this technique. And so there's, again, by about a factor of 3 to 5, we have the highest angular resolution in the world. So it's a wonderful lab. So here's a picture of Mount Wilson. I don't know, have any of you guys been to Mount Wilson by chance and visited? Nobody? Wow, I'm sure some of you have been to LA, so you have no excuse. Next time you should go. This is what it looks like, and there's the big 100-inch dome in the center. I'm going to have a video in a second inside that very large L-shaped building you see in the center there, right near the 100-inch. I mentioned a little bit briefly, but again, to do interferometry and to simulate a very large telescope, you really have to have the light beams simulate going through a large telescope, which is to say they have to have, just like a mirror has to have the right shape, right, to make a good image. The interferometer delays have to be that same right shape. And so you have to control the path of the light beams from the different telescopes so that they interfere that the path length through the atmosphere is equal between all the telescopes, just like a parabolic lens or parabolic mirror does, right, in your normal telescope. And so to do that, we need very long delay lines that can basically take the light from one telescope and park it and bounce it back and forth between mirrors many times in order to delay it, to wait for the light of another telescope to get into phase or to be, to match those time constraints, those matching constraints. So I don't know if you can see the 6 telescopes, but here's my little circle showing you them. They're only 1 meter telescopes. And you can see maybe a little bit that there's little pipes connecting them. And that is because we need once the light gets to the telescope, we have to send it to that central building, and we can't just send it over the air because there's too much, turbulence in the air. And also there's air, which gives you dispersion. And so we have to do that through a vacuum pipe. So those are kind of, if you're there and you're walking through the forest, they look like, light like aqueducts, like Roman aqueducts, except they're for photons across the forest. And here shows you the long baseline, 330 meters. So again, imagine this is one huge mirror surface, except we only collect light from these 6 small chunks of that large mirror. We have that, of course, means we don't have a lot of collecting area, but it does recover the angular resolution of such a large telescope. So this is kind of a cool movie showing you inside that building. Just so we're going to be, when I started, we're going to be looking at a long building at these delay lines that are used for bouncing the light around. And then we'll turn around and we'll look into the beam combiner room, which are a bunch of optical tables for these different groups, like my group and the Nice group, and have their own tables where they have their equipment. So let me play that. Okay, so there's the 40-meter long, these are like rails that we run the delay lines on. They need laser metrology to maintain the paths to within sub-microns over these long distances. This is a beam compressor and beam switch yard. And right there in front of you is the table that my work is on, and then this is other tables that also have, again, visible and infrared instruments. Now, just a little more detail about my instrument and how it works. Here is showing you 6 beams that are coming into the system. Now, at this point, the facility has done all this hard work of collecting the light, shrinking the light from 1 meter down to a beam of only 20 millimeters, so a factor of 50 beam compression, and it's delayed the light so that it has the right path so that we can do this magical interference. And lastly, it has done correction for some turbulence. It either uses an adaptive optic system on some of the telescopes currently, or just tip and tilt to stabilize the pointing of the beams. So the light comes through this and gets picked off by some mirrors. And if you look in the distance of this image, you see these pretty gold circles, right? Those are gold-coated off-axis parabolas, which focus these beams into single-mode fiber optics. So now we basically have taken a 1 meter beam that's come from space across, the galaxy, and we've collected it and we've delayed it, transported it, and shrunk it down into a 5-micron core of a fiber. Okay, now what do we do with that? So we have 6 telescopes, we have 6 fibers, each with our photons in them, right? So we need to now interfere them together somehow. And the method that we use is what's called an image plane combiner. So we basically take advantage of interference of light. And you may recall from optics that if you take 2 beams of light and you image them, you get a interference pattern like this picture on the left, right? If you had 1 beam, you would just get this blob. If you have 2 beams, you get interference, right? This is the wave nature of light, right? If you blocked 1 beam, you would get a blob. Block the other beam, you get a blob. But put them together and magic, you get this sine wave, which is your interference. And we can multiplex this because that sine wave you see there, the frequency of it depends on how far apart those light beams are. So if they're very close together, you get a very slow sine wave. If you put their beams very far apart and do the same interference experiment, they go very quickly. And so by having a pattern of separations that we call a non-redundant spacing if you can see it on the upper left, we have some sort of peculiar and specific spacing of our single mode fibers. We then can multiplex all the different interference patterns at the same time on the same detector. So that's kind of a clever trick we use to do 6 telescopes at once, which if you do the math is 15 baselines. If you look at the number of pairs of telescopes, we have to have 15 fringes or 15 of these sine waves all overlapping, but with a unique sine wave signature that we can extract the data later. Anyway, we have imagine we have these sine waves. Well, that's not very efficient to spread that light across the detector because there's actually no information in the up and down direction. So we squash the light into a line. So that's just using a cylindrical lens. So it only focuses in one dimension, and in the other dimension, it doesn't do anything. And if you look, you can see the fringes are there. They're just now squished into a line rather than taking up a big circle. And to add one more layer of complexity, we can now take that and think of it like a slit and disperse it with a prism. So what we measure on a detector looks like this, except not nearly so high signal to noise on a star, which are faint, but we see fringes that are wavelength dependent. So we actually can measure the 15 baselines of our interferometer, and then we can do it at, say, 8 or even more wavelengths at the. And one thing I'll show you is in our latest work, we're trying to expand that so we can do more and more wavelengths at the same time across a wider and wider range. Okay, so I guess before I go to some science results, are there any, questions about the technique? that you want to ask right now? Anybody? Or the facility?
Do you get a lot of loss from the atmosphere that's still above Mount Wilson, and if so, how much?
Well, sorry, you're asking, do we get loss from the atmosphere or just from everything?
I guess I'm thinking mostly the atmosphere, but it'd be kind of interesting to know what you still lose from before you get to combine the beams.
Yeah, that's an insightful question, because one of the real struggles we have in this method is in order to get from that telescope through those pipes, through the delay lines, through the beam compressors, into the fibers, through the spectrograph, there's like 27 surfaces. So even if you had a pretty good reflectivity or transmission, we are losing huge amounts of light, unfortunately. So in the infrared, where we can do a bit better job on coatings, we maybe lose, 85% of the light before it even gets to the fiber, which is terrible. And then because of atmospheric turbulence, we can only focus maybe a few. Without adaptive optics, we actually can only focus 5 or 10% of the light into the fiber because of turbulence, So yeah, the throughput on this system is really low at the percent level, which is terrible. And it's something that we wish we could improve, and people do work on trying to improve our coatings all the time. Now, the losses to the atmosphere in the infrared, when you're in these particular bands that we observe in, which like there you have letters like the JHK band, those are pretty high transmission, above 80% across the bands and higher in the middle of them. So that's not a huge problem. By far, it's our transmission of all of our mirrors and surfaces, sadly. So yeah, systems that have fewer reflections can have a very big improvement in sensitivity because of that.
Thank you.
Sorry, I thought I heard someone say something, follow up?
I just said thank you.
Oh, okay. Okay, so some science. So one of the early science cases that we did was to look at stars that are interesting for imaging. I mean, after all, most stars are actually pretty boring at the sort of most basic level to image, because they're just basically circles, right? If you looked at the sun, unless it had a really big sunspot, I mean, it would be very hard to detect a deviation from just a limb darkened disk, perfect circle, basically. And so a lot of stars are like that. So imaging stars that are like that, it's not, mostly all you can extract from the data is a diameter and a limb darkening coefficient, for instance, and look for any sign of spots. But there are some stars that do show a lot of interesting structure, and the one I want to mention here are what we call rapid rotators. So you probably know that stars that are early type stars, like A and B stars, have weak magnetic fields, which end up meaning that they can stay spinning for their entire main sequence lifespan. Stars like the sun have magnetic fields which generate angular momentum loss in winds. So the stars like the sun slow down over their billions of years in the main sequence, while these stars, these younger and more massive, these massive and not as old stars, just stay spinning at their birth spin. In fact, they spin up over time because they get smaller and contract. Anyway, was never observed directly before. We of course knew it was happening from spectral analysis, right? That you can see that one side of the star is blue shifted as it comes toward you, the other side is red shifted. So we can see from a high resolution spectrum that the spectral lines are broadened, and we know they're spinning fast. But we could never actually observe it directly, nor could we test our theories of what the impact of that rotation is on the shape and on the temperature. The basic prediction of what happens is that you expect the star heated, of course, like a pancake. Like if you something, right, it bulges out, kind of like how the Earth is oblate. This was first detected with the Palomar testbed interferometer in 2001, where they couldn't make an image, but they could measure the size of Altair in different dimensions in different directions on the sky and see that the star was longer in one direction than another. The star Vega was recently discovered to be a rapid rotator as well, but it wasn't identified earlier because its pole of its north pole is right pointed at us, and so even though it's spinning around at hundreds of kilometers per second, the Doppler shift is minimal because of a trick of the geometry, that it's directly in the plane of the sky, and we don't see the Doppler shifts. But what we do see is that the edges of the star are very dark. This is an effect that's called gravity. It was predicted, again, never before observed before interferometry, but it's called gravity darkening, and that's because when the equator starts to bulge out, you can think of it as the equator now is going to be 10 or 15% farther away from the core. And so the heat that's coming out of the core, right, it gets colder as it expands and goes, gets away from the star. The energy density goes down, gets colder. And so the equator, which is farther from the star, will be cooler, while the poles, which are closer, will stay hotter. And so this was an effect predicted. Now, the first image of that effect is what we did back in 2007 starting with Altair, which you all know, I'm sure, well. It's a very nearby, one of the nearest, maybe the nearest hot star, 5 parsecs away, very rapidly rotating. And this was our image that we took using this instrument at Chara. And what you see, right, is that the star is oblate, right? It's longer in one dimension than before, which was already partially known from that other interferometer. But what we could add to it was we could see that the brightness changed as you go north to south, right? And you can see that the pole region is much hotter than the equator. In fact, it's over 1,000 Kelvin different in temperature, which, if you know anything about stars, is quite big. That's as much as an entire spectral type sometimes, going 1,000 different. So in fact, the top of the star at the north, the pole of these rapid rotators can be like an early type, like an A0, while the equator could be like an early F star or something, right? It can really change by a huge amount. Here's a model that we made of Altair. So this is what a star looks like, just a normal star, not spinning. You see it's a little darker on the edges, and that's the so-called limb darkening effect. If you start to spin it up in this animation, you'll see that at some point, as you get closer and closer to breakup, it expands along the equator and cools down. And now I can show you the model versus the data for Altair that we used in interpreting our images. Now we can do this to only a handful of stars. Chara, although it is the longest baselines in the world, Altair and Vega, for instance, are really especially close. And then there's another 4 or 5 that we can do a bit, and then we kind of run out of objects and we need a bigger interferometer. But this is a nice gallery, I think, showing what we found of our images. Here's Altair. That we observed Alderaan and Rosselhague, Regulus, and lastly here, Beta Cas. And this is just ordered by spectral type here. And you can see they're at different angles, but they all show this elongation and gravity darkening effect. And, we learn more by studying this as a function of different temperatures and angles to figure out if theory can explain what we're seeing here.
The uppermost bright spot on Altair, is that a flare?
Good question. We think it's just it's a level of the noise. We don't think it's real because for instance, this star rotates every 8 hours, and so it should move if it were a real object, and we can look at data taken at different times and see that it doesn't move like a spot, and that it's most likely an artifact or noise in our limited data that we have. But good question. We are interested, Altair actually might have some spots, so we are interested in following up on that over time when we can. And by the way, the scaling here is their size in this case. So that's what this shows. How it shows you the relative sizes in actual, solar radii. You can see a scale at the bottom of what the size that scale at the bottom is the diameter of the sun. So you can see all these are a bit bigger than the sun, of course, since they're more massive early types. All right. Oh, I didn't get into the details, but one of our conclusions of this is that this gravity darkening effect that we mentioned earlier was not as pronounced as the theory. So there was theory that predicted how dark the equator would get, and we find that it generally doesn't get as dark as expected. And since this time, there have been now new papers written to try to that claim to explain that through better theory and better models of solar structure. Now here's another cool object. I'm sure many of you know, Beta Lyrae. It's a interacting and eclipsing binary, right, with about a 12.9 day period. Here are some light curves of what you see, and it has a massive star that's that is losing mass, and it used to be a massive star, but it's lost a lot of its mass and given it into a disk around its neighbor star. So it's a complex source. This is our first image that we made of it, and you can see the scale here. Its separation is only about 1 milliarc second. So now we're really getting, into pretty small angles here, right? That's 1,000 times smaller than, typical image that you would see in your scope, right? So very tiny. Now, one neat thing about when you have very high angular resolution is the universe is dynamic, right? Because you're zooming in so much that things are changing. And so this was our first movie that we made of an interacting binary star. So let me start this movie off. Hold on, it should start here, I hope. Oh, there it is. Okay, here's our movie of half a cycle here, showing a little bit of the details of this disk. And if you look at the dark object there, the darker one, you notice how it looks a bit egg-shaped, or teardrop-shaped. Well, this is actually the first image of a Roche lobe filling star. So you probably have seen these images of interacting binaries that when a star grows and it's so close to another star, it starts getting distorted in its shape as the gravity of the companion starts, pulling on it, and you get these teardrop-shaped stars. Well, this is actually, we think, the first image of seeing that for real, not just in the simulations. And then we have a similar story with Algol, another well-known object. It's a much shorter period, and it's another eclipsing system, but it's what we would call a semi-detached system. That means, it doesn't have they're not totally touching each other, and they don't have a disk around one. They're close enough that they're interacting, and one star is distorting the other, but there's not as much material between them. So this was an image we took out of eclipse, and you can see a movie of more of the images on Wikipedia. But one of the neat things is we kind of got lucky one night, and we took our interferometer data right during an eclipse. And this is what the image looked like here, where you can really actually see the cooler star B in front of A and blocking part of it. And I think it's pretty amazing that you can see that in this image. And even though we can know that from interpreting the light curve, it's neat to see it. Epsilon Aurigae is a very unusual system. I don't know if you guys have followed it, but it has a very bizarre eclipse that happens every 27 years. It was discovered over 100 years ago, this eclipse, back before there was anything but, visual observers. And interestingly, every 27 years, when you read the literature, is neat because every 27 years, there's new techniques in astronomy, right? Like maybe in 1880, maybe it was the first photographic data on it, or then it became the first spectrograph data on it. In the 60s, there was the first X-ray data, or et cetera, et cetera. So it's neat that every 27 years there's a new technique that advances our understanding of the system. And this year, or last time around, in around 2010, I think interferometry was the big new technique that came onto the scene and was able to add to the story. So what makes this weird is first of all, you probably know that eclipsing binaries are usually a very short period, right? Because you need to have a very good alignment with the two stars so they eclipse. Well, this is a 27-year period, which is unheard of for an eclipsing binary system, because the odds of a 27-year orbit being just aligned with each other is almost nil. However, this isn't just an eclipse of two stars. This eclipse lasts for 2 years and is understood as being caused by a disk around one of the two stars. So it's not two stars by themselves eclipsing. One star has a very big disk, like many astronomical units, and so the odds are higher now that they eclipse, and that's why it lasts for so long. Now, I won't get into why it's such a mysterious system, but it is a weird system because this second star that has the disk around it has never been directly observed. So this disk seems to be completely blocking it, or perhaps it's a black hole or something like that. So it's pretty interesting to get to the bottom of it. Now to explain the data, in 1980, the last time there was a good modeling done before the recent one, this was the model that they think you should see if you could image it. It should be the second star is hidden behind a disk, and the disk is, again, a few AU across and very thin in dimension. And again, and that has to do with the shape of the light curve and how the dust particles block the different wavelengths. And it's, again, it's a pretty complex analysis, but this is what they predicted we would see. So in 2008, when the next eclipse happened, we had taken some data before the eclipse, and this was our image. It was just kind of some more or less boring circle. Maybe that variation you see there could be real, or maybe it's just noise is kind of near the limit, but it basically looks like a star. And then we started taking data during the ingress of the eclipse, and the first image we took, it looked like this, which, does kind of look like, somebody is putting their finger across the star there and blocking just a part of it. And it looks remarkably like the model, right? The Kemp 1980 model down there shows this thin disk that starts to go into the star. And indeed, as we took more data, this little thin disk just continued to go across and get bigger and bigger until in February you can see we actually see half of a star, which again, I couldn't believe that this is what we saw. Now we continue to take data over the 2 years, and Brian Kloppenberg, who wrote this up as part of his PhD thesis at the University of Denver, he created this really beautiful way of looking at the data that I'll show you. So instead of normally we would make a movie like I showed you, and you can see the disk moving across the star. Well, what Brian did, which was I thought really nice, was he did something where what he did is he took the model of the motion of the binary star so that you could, instead of freezing the star and watching the disk go across, what you do is you freeze the disk in the software, and then you let the star move behind it to give you an image of the disk in silhouette. So what I'm going to show you now is what happens if you take the data that I showed you, but then instead of making it a movie, you move it to represent the motion of the disk and add it all together. And so this is this is now the star moving across the disk in the orbit and outlining this incredibly thin and sharp-edged disk, just as Kemp predicted. So this, again, I just find this incredible. I mean, this is such a weird object, and the fact that it happened just at a good time that we had the technology and that it's bright and nearby. I mean, it's just a fortuitous and incredible opportunity to learn about this star. This is what astronomy, I'm sure you know, is full of, right? Weird things and coincidences and good luck. So it happens all the time, luckily. All right, you mentioned at my intro that we also been moving towards understanding stellar magnetism, and my student Rachel Rutenbacher did a great PhD doing the first imaging of magnetically active stars. So these are not, rapid rotators in the sense of being like the hot stars, but these are giant, they turn out not to be solar type stars, but they're giant stars that are spun up by a binary, which reignites their magnetism. So these stars are extremely active, way more active than the sun, much more similar to how the sun may have been in the first few 100 million years of its life. Super, super strong magnetic fields and spots. And so we were able to watch this star, and these stars are in, like I mentioned, they're in binary systems. They're actually spun up by the binary. And in this case, it's an 18-day period. And so Rachel took data over that 18-day period so we could watch the spots as they move, right, across the star and reappear. And so we could make a three-dimensional model and movie of that. And so here is our model, or image. But now, instead of being an image, one-time image, it's, oh, sorry, let me find. No, it's not moving. Well, it should move. Sorry, I don't know why it's not moving. That's too bad. Oh, there it went. I think I saw it move. Ugh. Sorry, guys. There's some problem with my movie. All right, the other movies work, but this one is not working. Sorry about that. Shoot. Oh, there it went. Okay, now it's working. Okay, you can see it. So this is showing you now all sides of Zeta Andromeda. And we see that there's kind of a dark patch on the pole, which is interesting why you would have that. I mean, the sun doesn't have that, for instance. And we then see some other bright spots. And one interesting thing we noticed is that the spots have no real symmetry. Like the spots are just big on one side or the other side. Unlike the solar dynamo on the sun, which are very symmetric, the magnetic activity at least is symmetric and concentrated in certain latitudes during the solar cycle. In this case, we don't see that kind of symmetry, which, again, this is a very different star than this current sun. It's not necessarily meant to be the same, but it is certainly interesting data for theorists who simulate the solar and the stellar dynamo to try to explain it. And then there's another object we were able to do, Sigma Gem. One neat thing about Sigma Gem is we were able to detect its companion. So these little ellipses show the orbit of the companion. And sure enough, when we imaged the spots on it, it was spinning in a way that was very much aligned with the orbit, as you would expect. So this is the spotted image of Sigma Gem, and you can see it, and that's the scale, with the companion around it at a highly inclined, position angle or inclination. All right. So just finishing up a few other random things, we can image the first few days of nova explosions with this method. So this was a nova, Novadell 2013, and this was our imaging we did over the first week. And you can see how it started very small and expanded. And unfortunately, as it expands, it starts to become optically thin and fainter. And at some point, it gets too big for our method, and we lose it. We can't observe it anymore. But we are able to observe these very early days, which is neat because those early days are when the explosion is dominated by the material, the ejecta from the actual explosion. Very soon after the explosion, the gas and the ejecta sweep up material around it and changes, the evolution. And so it's kind of neat to see a snapshot here before that happens. Now, recently, we've been doing most of what I just showed you was before our new upgrade. So that was work up to about 2018. In the last 3 years, we've done some major upgrades at Chara. We've added adaptive optics to the telescopes, which can improve our sensitivity. We've acquired some really new breakthrough detectors that have over 10 times better read noise performance. We've upgraded the optics in addition to the camera and added some more modes. Just this month, we delivered a new instrument called Mystic, which expands the reach and farther into the infrared, out beyond 2 microns of wavelength. And we've debuted some new precision modes, and I'll show a couple of slides on that now. This is what our new instrument Mystic looks like. What makes it difficult in the farther infrared is that you have to put it all inside of a cryogenic dewar and cool it down to 200 Kelvin. And so that definitely was a challenge for us to learn some new methods of how to do that in a cryogenic and vacuum state. So this is a cool thing showing this I mentioned this new camera as a breakthrough camera, and I really am not kidding. What they were able to do was add an Avalanche Photodiode to every pixel of this detector. Now, I don't know if you've heard of that detector. An Avalanche Photodiode is where you put a high voltage across a semiconductor, and so when a photon creates an electron, this high voltage causes an avalanche that accelerates that electron, which knocks off more electrons, which knocks off more electrons like a photomultiplier tube, and creates a huge number of electrons. So you start with 1, but here you end up with, say, 30, a gain of 30. And so that means you boost your signal, and so when you read out your detector at high speed, the read noise, that you always have becomes proportionally less, because read noise is going to always be the same, but here we boosted our signal by a factor 30. So this graph here shows you how it looks if the detector was normal. And this next slide is all we did was increase this gain. We didn't change the light source. We didn't change the integration time. All we did was increase this avalanche gain. And it goes from here, which you can barely see anything, to here, where I think you would agree that is kind of an amazing improvement for the same exact light illumination. So this really has boosted our sensitivity by more than a factor of 10. And this is just showing us last month, we finally were able to get to Chara after 2 years of COVID, or a year and a half of COVID delays, and we were able to put our new instrument on. And now we can observe from 1 to, not 1.24, sorry, 2.4, that was a typo, 1 to 2.4 microns all at the same time with one shot, which really increases our productivity and gives us more, more science we can do, of course. And I guess if you, so the new stuff we've done with that is one of my students is looking at looking for exoplanets around stars by looking for wobble. You know that if a planet has a star around it, gravitationally it causes that star to wobble around a little bit. And so what we do is we look at, it turns out, 2 stars that are orbiting each other, because we can measure their separation very well with Chara, and we look for wobble. Just to show you how good our precision is, this image on the right, you can see that if you look closely at the scale, the entire scale of this plot here is around 0.2 milliarc seconds. So the entire range is zoomed up to 0.2 milliarc seconds now. So really zooming in. And we can watch a star moving every, say, 10 minutes in orbit. So that at the bottom is where we detected it at the beginning of our data. 10 minutes later, it moved, and it moved again, and it moved again. And if you look at this separation, we are measuring a relative position of these 2 stars down at the less than 10 micro arc second level. Now that's the kind of level you may recall the VLBA Event Horizon Telescope had when they imaged the Event Horizon around the black hole from a few years ago. And so what we can do, again, is look now for a deviation from Keplerian motion that tells us there's a planet there. And just, again, this is work in progress. Unfortunately, I can't show you an exoplanet. I wouldn't do it on YouTube anyway. With Tyler would do it as part of his thesis. But I can show you these published results of Kappa Peg, just to show you the breakthrough in precision. On the left is a star that was observed, a binary star that was observed, Kappa Peg. Kappa Peg has a known companion, not a planet, but it causes a wobble of around 1 milliarc second. So again, pretty small, 1 milliarc second, okay? That, and you can see there on this slide so far, the data from Munterspaw et al., which did an amazing thesis working on this about 15 years ago. Now with our new method, which is more precise, here's the exact same star, but with our data, looks like this. And if you look hard, those little teeny black ellipses, those are our data points now. So rather than these, circles that you see on the left, we actually now are doing like 50 times better in precision, and that gets us into the domain of trying to find exoplanets now. And my last result is preliminary, because this is a relatively new upgrades and we have a lot of work to still do on our data processing. But we're looking at also planets forming and how planets form around young stars. So these are stars that still have their disks of gas and dust and are forming planets as we speak. And it's turning out to be very complex. As you probably know, there's thousands of exoplanets found, and they're very diverse in properties. And this suggests and is true that the planet formation process is complex and random and difficult to fully understand. And so the closer we look at the sites of planet formation, we do find more and more complexity. So for instance, this is a star called Avia Auriga. If you look at it with the ALMA array, which is in the millimeter, this is sensitive to large grains, like millimeter-sized grains of dust, out of which planets can form. And you look at it, and it looks like there's a ring, right? And there's a mist, and in the middle of this ring, which is about the size of our solar system, there doesn't appear to be very much going on, right? If you just looked at this. Now, that's misleading. It just means there aren't very many big dust grains that are millimeter. In fact, if you look at it in a different way, using the VLT instrument called Sphere, this is what it looks like in the infrared in scattered light. So again, the left shows you big dust that are in the process of maybe forming planets. It looks like there's nothing left in the center, but in fact, these large dust grains are presumably now been crushed up a bit or have been grown into planets themselves. And look at that amazing structure and spiral structure we see in scatter light. And then with Chara, we're actually going another factor of 100 deeper. And this is one of our preliminary images. I don't know if this will be what we publish someday because this is super early analysis, but this is an image from Chara where we zoom in right next to the star on a scale of an astronomical unit, you see, and we see the hot dust very closest to the star. So with all these methods, we can probe this factor of over 100 in scale, and using different wavelengths, we can probe different parts of the planet formation puzzle. All right, and that's Ben, my student, Ben's thesis, who's been working on the instrumentation and some of the modeling of these sources. And Stefan Krauss made this image. I should give him credit for that since it's not published yet. All right, well, I probably have gone on too long, but there is to go beyond this, we really need to go to the next level if we want to go deeper and not just look at these disks like that, but let's say we want to actually look at the planets themselves. Now, if we had more sensitivity, we could start to look at all sorts of things going on in planet formation. We could look at the planets themselves as they're forming. We could look at the gaps they carve out, right? We could look for outflows. We can look for even circumplanetary disks that are orbiting the disk, like the Galilean moons formed out of a disk going around Jupiter, right? We have the potential to actually image those disks themselves around young Jupiters. Now, unfortunately, this is not going to come cheap. We did a lot of studies with my colleagues for the planet formation imager to see what we could do. For instance, let me show you a couple simulation. If we wanted to look at a young system forming planets, if we had 21 telescopes that were 4 meters in size, we could measure the gas giants forming around all the nearby star forming regions. So upper right shows you the star, and then it shows you these 3 exoplanets down to Jovian mass that we simulated. But 21 4-meter telescopes is not cheap. It might be doable, but it's not cheap. Now, if you wanted to be more ambitious and image planets around stars down to the Earth, to the solar system, we did a simulation of what the solar system would look like, with Jupiter and Saturn. And this shows you this helped us figure out, well, what kind of system would you need if you wanted to image, for instance, on the bottom right, you see a gap, a little donut. That's a gap opened up by this young Jupiter in our solar system simulation. Now, to do that, we would need large we would need 12 8-meter telescopes. Now, you know probably that an 8-meter telescope runs you around $100 million. So this is not affordable with the current budget. Now, maybe you could reduce the price by, buying in bulk, but it still is going to be a huge cost that we don't really have in the National Science Foundation budget at the moment. So we're going to try to improve technology on telescopes to try to bring down the price, make bigger telescopes cheaper. That could help. And we're also interested in seeing what we can do in space. If you're in space, you can use smaller telescopes. Although space is more expensive in general, maybe in this particular case, it might be cheaper because, you can just fly the telescopes in space. It can be smaller. You won't need all those delay lines and infrastructure. And maybe this is one case where space interferometry, a space version is cheaper than the ground-based version. And with that, thanks for your patience. I hope that you've recognized some of your favorite stars, and I'll take any last questions you might have. Thanks.
I don't know if it's high enough in the sky, but assuming it were, the way your chart is set up now, would you be able to get any extra information on the Fomalhaut and its system?
We have, VLTI has observed Fomalhaut, and try to figure out which direction it's spinning. So Fomalhaut has been observed by interferometers. I feel like we can't do it at Chara. What's its declination? It may be too, I can't remember its declination.
I don't know offhand, sorry.
It's okay. But yeah, Fomalhaut is definitely an interesting source of the debris disk and trying to understand its geometry for sure.
Not really a question, but a comment, but I am just absolutely amazed at that silhouette of the protoplanetary disk that you got.
Mm-hmm.
It wasn't just lucky, but the skill and everything involved with that, just amazing.
Yeah,
it really looks like what you'd expect.
It's just really crazy that it happened. I mean, the odds seem so against having that be the odds of it being close enough, and that we would in that angle. Because imagine how that would look from any other angle too, right? It wouldn't look like that at all. So it's like this really, really weird coincidence. I can't kind of wrap my head around the odds of that one.
Well, with the plethora of stars in the universe, or at least in our galaxy, you would possibly find all kinds of combinations are possible. So we would just have to have the technology to do so. By the way, Fomalhaut's minus 30 degrees declination.
So we can't do that at Chara, right. But the VLTI is in Chile, and it has observed.
Actually, considering the precision you seem to be getting now, you think you could even find out something on some of the relatively smaller but more closer stars like Sirius?
Yes, definitely. There's many other naked eye and famous stars that we can observe. Sirius is actually pretty big, I think, compared to these stars, actually. I think, if I remember right.
The main one is like 2 solar masses, and the pup's 1 solar mass. That's
okay. So, but they're, like I said, the thing is that most stars are unless there's something weird going on with them, are just basically circles, right? So it's not, it's not super exciting or easy to get observing time if you just say, I want to observe it because it's a famous star, but it's probably boring. You can imagine that doesn't go over well. So you have to find something interesting. I think, Chara is cheap compared to big observatories, but it's still estimated cost is around $5,000 a night. So it's not that cheap. A 10-meter telescope is like $50,000 a night. It's like $1 a second. So we're more like $1 every 10 seconds, but it's still, it's oversubscribed by a factor of 4 to 5. So there's only 1/4 of the requested observing gets done in a given year at the current rate. But if you have any requests, you let me know. Tell me what's interesting. We can try to sneak it in. One good thing about when you're a builder of an instrument, you do have more time that you can observe random things, like because we get a more observing time, and we have more freedom since we are working on the instrument to do something for engineering. We can do some engineering time because we write the pipelines and we might need a test object. So we get to sort of sneak in some fun objects more often than the ordinary astronomer sometimes, which is also fun.
Any other questions for John?
Excellent talk. I enjoyed it quite a bit.
Yes.
Thanks, guys.
Agreed.
Well, hopefully it'll be, I'll talk to you again soon. Oh, I was going to say, I don't know if anybody in this group, does anything that could be relevant to what we do. Like, since we do observe a lot of naked eye stars and relatively bright stars, sometimes there's opportunities for collaboration, since sometimes they're variable stars or there's outbursts that happen or whatever. So if anybody in this group ever has an idea like that or wants to participate or is interested in photometry or monitoring, just send me an email. We can discuss whether there's any overlap of interest.
Very good.
Thanks again, John.
Okay. All right. Well, nice to see you guys. Bye.
I do have, before you go, one final question for you. We like to give our guest speakers a little token of our appreciation, which would be a club T-shirt, which looks like this, basically. Or we also have two different styles of hats. There's sort of a, if I can get it lined up right, a standard kind of hat, or we have these low profile kind of floppy type ones. What would you like?
T-shirt, please.
T-shirt, what size?
Large.
Large, okay. If you could just send me your shipping address, we'll get that off to you.
All righty.
And thanks again, much appreciated.
Bye.
Thank you.
Thank you, John.
Okay.
Video.
A second here, I'm gonna try to get back to my normal view. There we go. Okay. So, moving on to officer reports, I just have one thing that I wanted to mention. As most of you know, a few years ago, UofM astronomy professor Sally Uli started a group called Michigan Dark Skies with the intention of getting the city of Ann Arbor to pass a outdoor lighting ordinance. We actually had some longer term goals than that, and that was to even maybe move to the state level. But of course, you got to start out someplace. So we started with Ann Arbor. There are several members of our club that are involved in this. They're members of that organization. You might remember a few months ago, Ryan Farber, who was our speaker. He has also been very involved in that group. But some of you already know this and know what I'm going to announce. But I'm very, very pleased to say that on September 7th, this was finally brought to the city council itself. I really expected that something this major, there'd be something to make them table it for a little bit, but instead they passed it unanimously. So, city of Ann Arbor has a lighting ordinance.
Wow. Fantastic.
Yes, very, very good news.
When did it act?
Yes. And I sent much compliments to Sally Wu. She really was on top of this. I don't know how she found time to do it, but she did. Her leadership was invaluable, but a lot of people had some input. So,
well done.
Mission accomplished. So with that, I will move on to other officers. Joy, do you have anything?
Can I ask a question on that?
Yeah, go ahead, Doug.
Was there a policy level provision that could be replicated for other towns?
Oh, absolutely, yes. Yeah, this was something that had been worked on, modified. It actually got delayed once, but for a good reason, and that's because the city started also working on a revision of their signage ordinance and realized that signs get lit up too. And they didn't want to have something in the sign ordinance that was inconsistent with a lighting ordinance that they anticipated might get passed in the near future.
Okay.
But that got all resolved, and it was actually an extra benefit. But we used some different models. I think maybe from the IDA, I'm trying to remember now to do this. And I'm sure we could get copies of the final product that the city passed. And absolutely, that could be used as a template for other communities, yes.
Yeah, I'd be interested in that.
Yeah. In fact, I'm going to see if maybe I can't get Scio to make some improvements. I was recently asked to be a member of this new group called the Scio Township Environmental Sustainability Task Force. And so this was something I couldn't really refuse, although I tried in a way, but I couldn't talk myself out of it. I actually got put into a group, in fact, at least temporary head of the group, that's dealing with materials and recycling, that kind of thing, attempting to hit like a zero waste goal. But there's another group which I want to at least influence that is going to deal with buildings and infrastructure. And my suggestions there are going to be ways that Scio can actually improve the outdoor lighting regulations they already have. We actually do already have a lighting ordinance that's woven into our zoning ordinance. But I can think of ways, and if I'd gotten a second term, back when I was supervisor, this was one of my goals to see if I could strengthen that. But being that I'm also a member of the larger group, I can get some of those ideas out to the people that would be dealing with that kind of thing. Like one thing I want to strongly recommend is to encourage people to use motion sensor lighting if they have to use outdoor lighting. In fact, I already had a chance to speak to the Planning Commission recently after Sally Uwe did a presentation to them. And that was to encourage them all to take a look at 3 places in Scio Township, Meyer, Lowe's, and Menards. Meyer did a fairly decent job when they built their place. They've got full cutoff fixtures, etc. Lowe's across the street from there did an even better job than Meyer. And it appears that they reduced the amount of lighting or the brightness of it at some time during night. And then Menards trumped them all. And about a half hour or so after they closed, they turn off their parking lot lights completely. And like I pointed out to them, you can check the records, but to the best of my knowledge, there hasn't been any crime wave there. Nothing's been of any harm. And if somebody was doing something in that lot, as soon as they turn a light on, they're going to stick out, whereas before, nobody would have probably paid any attention to it. So we have some models. There are some things that could be done that are fairly aggressive. But anyway, I digress. But as a result of this, it's more inspiration to see what we can do in some adjacent communities. So, and part of this task. Yes, go ahead, Amy.
Oh, I'm sorry. I just wanted to interject really quickly that I don't know if you've heard the news, but the library just bought a very large space out there, one of the warehouses at, I think it's 265 Parkland Plaza. Okay. And within the next year, they're going to be building a big archive office space, building out from the building that's already there. So any, information you can send to pass along for how we should deal with our lighting there, any model, any other information I can pass along, I'm happy to do that.
Yeah, they're going to run into that as soon as they start doing the application process.
Yep.
So, yeah. See, John wants to stand up?
Yeah, Charlie, just parenthetically, I live in Genoa Township.
John, can you turn your volume up?
I don't know, I can speak louder. Is that any good?
You're still pretty soft.
Oh, I'm sorry. But if I live in a township that has a lighting ordinance, and it's important for citizens to watch developers and individual builders to ensure that the lighting ordinances are followed. Law is no good unless it's enforced. And the other thing is to encourage the lowering of the temperature of these lamps from the 5,000 degree to the 4,000 degree area. And, these are two factors that individuals can have some input in with their local authorities.
Thank you. Okay. So moving on, Joy, do you have anything to report? Well, we lost your sound again, but we caught what you said, and thank you for doing the minutes. Very much appreciated.
This time you weren't unmuted.
Didn't I see Joy unmuted when she tried to speak?
Yeah, she was.
Yeah.
No.
Yeah, you lost sound.
Never mind.
Yeah. Okay. Liz Calhoun was not able to join us tonight, but she did email a report. And I just happened to have that here. And she was quite concise and just said that she is working with Doug Scoble regarding the receipt and distribution of all the calendars and RAC guides, etc., that Doug is going to be ordering. So he's going to ship all those to Liz, and then she will arrange with the individual people to, she said in email, meet them halfway or they can go to her. But she's going to handle distribution down here for us. So, and since I'm reading reports, Adrian also was not able to join us, but he sent a report in. And he says that he was working with Doug on the handbooks and calendar info. He's actually a member of RASC, so he got us a key contact, actually got us some important information. He also wanted us to know he's continuing to be part of the Explore Scientific Global Star Party, which occurs every Tuesday night. He sent along, and we can forward this, a link to go there, or it's on Facebook and YouTube. And a reminder that Astronomy at the Beach will take place on September 24th and 25th. In fact, Brian might speak a little bit about that, and he sent out some information about it also. But he also, as in Adrian, adds that he has a friend in Argentina, Maxi Faleres, I probably mispronounced that, who has agreed to do either a live viewing or image share of Southern Hemisphere skies. Now that would be a cool touch, wouldn't it? Anyway, that will also, of course, be an online event. I think that'd really be neat, especially if they can do that, actual viewing. About extending our reach, huh?
I put the 2021 URL for Astronomy at the Beach in the chat session if anybody wants it.
Cool, thank you, Jeff.
Mm-hmm.
Okay, so Dave Jorgensen.
Yeah, Shirley, I've got nothing to report.
That was quick, Dave. Thank you much. How about our guy with the money, Doug Scoble?
The guy with the money. Can you hear me?
Yes.
Yeah. Okay, good. So speaking of RASC calendars and handbooks, after an absence last year, they're back on this year, and the good news is that they have reduced their prices significantly. The rep I talked to on the phone said they're trying to accommodate the U.S. market a little better, and they're going to be shipping differently too. They were having a lot of damage issues that I had problems with too. So anyway, I sent an email. If I didn't get the email, the calendars are $16 each. The handbooks are going to be only $21 each, which is pretty inexpensive compared to recent years. And as Charlie mentioned, I'm going to be doing the ordering, so people send their money to me, but I'm going to have them shipped to Liz, and she will handle getting them to the members that order them. And you'll have to work it out with her, but that probably won't be until November or December, assuming that we're not meeting in person by then. If we are, that'll make it a lot easier because she'll just bring them to the meetings. That part is settled, and but the only other things are we're still at 169 members, with the caveat being that about a dozen of those are folks we've been carrying because of the provisions we have for the COVID thing. We haven't expunged anybody since early last year. But only 12 that we're carrying, which isn't bad. I think that's pretty good. Most people, the rest of the membership should be, I think, commended for continuing to pay dues, and just thank you for doing that. And no big expenses this past month, other than paid to mail the shirts to Jody and Roy McCulloch down in Ohio for doing their talk in August, and also some money, like $58 and some change to Jack for paint for the observatory to cover up the graffiti. Hopefully it's still covered up and no new stuff. And that's my report.
Thank you, Doug. How about Jack?
Oh, here we go. I'm going to go on shared screen. Make sure we get this. Okay, are you able to see this?
Yep.
Yes.
Okay. Now, do you see the tree?
See the tree.
Yeah.
Okay. I'm asking this, so I hope I'm coming through so I can explain this.
Yeah.
This is on the road going up to the Radio Observatory. This is on the side dirt road. Now, the reason for this is not cut down, this is broken off. And this is what was left on the side of the road. This is quite a large tree, but it's very similar to the trees we are working on next to the observatory.
Oh.
This just happened end of August. Some of you are familiar in the Pinckney area where they had the thunderstorms and some other types of rainstorms and windstorms and that. Well, this is what happened out there, and I guess university had some people come out and cut this tree up and move it off the road. Okay. With that in mind, we move up to the Radio Observatory. And as you can see, some of you recognize this new fence here because of our little vandals have torn it down and ripped it apart. So they did repair that. That was kind of nice, getting that taken care of. As we move on. Now, about that graffiti that Doug talked about. Yes, the paint did work. I had some other blue paint you can see here. We took off the numbers here that they painted. And the other graffiti they had on this side of the wall has been removed, or I should say painted over. The elastomeric paint, if you put it on really thick, works well. Because if you read the background on the paint, it's designed to be used a couple of times on a surface to make it elastomeric, where it will stretch with the surface. So by putting this paint on heavy, it covered up the red. And as you can see, this would be the south side where they had that big red AUW or whatever, and the bird looking here and all that. We'll see over the wintertime how well the paint works, covering everything up. And you can see on these, this would be the west wall facing the west side. And this is where there was a lot of graffiti through here, different painting, coloring, reds, greens, everything. That's gone. So if you have last month's newsletter, you can compare this with last month's newsletter. Yeah. Now, we're presently working on these trees that are next to the observatory. and we've cut down some more. We just had a meeting Thursday. 3 of us were out there and cut down a few more trees in that. We are moving these out and stacking them in certain areas, and then we'll be cutting off this area down here. The other area has already been cut and cleaned, but now this area is going up next to the observatory. You might recognize the path. Some of you from coming off the side of the observatory door, you walk down out here. These are going, and the other large trees around the wall is going to be the other large trees along the side of the observatory. We're working on those.
No, this is the east side of the observatory.
This is the east side, correct. Yes, this would be the east side. And this is the side where you have a lot of tall trees. Hopefully once we get rid of those, there'll be like a little corridor that will open up, and that will be free of the trees. And then that will also give you a little bit more observing room too, a little more night sky to look at. Yeah. But when you think of the other trees that have fallen down around there and you look at the ones we've got, it's an accident waiting to happen. So we're going to work on this. But that, just we clarify something. All we're doing is the trees around the observatory. These other trees you see back here and stuff like that, and these trees way down here and that, we're not fooling around with that. We're looking at the ones that are going to be in probably a 70 to 80 foot range from the observatory wall, because some of those trees are 70-some feet in the air. There's some tall trees there. Any more questions about anything?
I have a question for Jack. How did you get that one tree that we cut down that got hung up? How did you get that thing out of there?
Very good. Okay, good question. John understands this probably better than anybody. We were using cutting and pulling trees down. And by the way, one way of coordinating a fall is we were using a come-along or a cable puller with some straps, and using that with a chain to guide and make sure the tree falls a certain position. It's sort of like making sure that we can guarantee where a tree falls to make sure we don't have any problems with it going the other way and hitting the observatory. But anyway, tree John is talking about was a big tree. We got it to fall down, but it ran into some other branches and didn't fall all the way. We tried to pull it down and it got hung up in the branches from the other tree. I went back out there and found a different area where there were some other tree branches that came up holding it. And I'd have to take out and show you. This particular photo doesn't show it because it's more over here on the right. But anyway, I went in and I cut those branches down. I chainsawed them down. And all of a sudden, out of nowhere, I heard the cracking, and the other branches that were holding it up gave way, and the tree and the whole thing just hit the ground. So, kind of like a science fiction movie, you know. But anyway, we have a tendency to use straps and come-alongs only because we want to control where a tree falls. Like I know in the movies they show the guy with his axe cut the tree down, guy that could go anywhere. Well, we're not doing that. That's not what we want. John can attest to that. And the other guys that were out there, Chris Adams and Mike Hagan were with me the other day. Thursday we're out there. And all those trees were pulled down and strapped down to make sure we had a controlled fall using the come-along. So, yes, we did take care of it. It's down there. I don't have the right photograph to show you the results, but you're welcome to come back out when you get done with your surgery and everything. I just got done with my other eye. I'm doing my left eye surgery this Wednesday. So, and it's going to rain all week out there out in Pinckney, so I don't think we're going to be doing too much. This is another problem we've had. We had some actual days scheduled, and supposedly it was going to rain those couple days. Then our scheduled days were supposed to be clear, no rain. And I got a phone call, or I should say an email in the morning from a few people saying, hey, it's raining out here in Pinckney. Are we still on? Or are we going to try and do this? And I told them no. And they told me it did rain the rest of the day. So this rain has been complicated. You go to 2 or 3 different places. They can all tell you, no, it ain't going to rain in the morning, or it's only going to rain till 6 or 7 o'clock. It won't rain after that, but that's not what happens. And these other trees that you've seen come down, I showed you, those are the thunderstorms, and people have told me they've actually seen what looked like a tornado funnel, but I don't live out in that area, so I'd have to rely on the people who live in that area, what they saw. So, this is what's going on. I went out and painted and took care of the graffiti. And that's what you see down the side of the road. And that is a memory of why we're taking those trees away. So, any more questions?
Is there any way to get that big tree limb further off of the road? Because during the day it's not a hazard, but at night I think it would be problematic.
I went out with that tree. This here is like 12, 14 inches diameter. This is a big tree.
Yeah, it is.
And it's heavy. And I have one alternative way of moving it. We either get 4 or 5 people with pry bars and try and move it, or I tie one of our straps, run it to one of the trees up here with the come along, and actually physically pull it up to the side of this mound here and pull it out of the road that way. You could probably pull it up and pivot it off this end and angle it right up, pull off the road that way.
Yeah,
but it is heavy.
Moving it a foot would be a big difference.
Yeah.
One thing we can do, Jack, is one thing we haven't used timber jack. I should give you my timber jack to use out there, but that can be cut up. And anyone who eats with wood and has a double-walled chimney, you can burn all the pine that you want, all the fir trees and pine that you want. It's not a problem. There's an awful lot of really good fuel lying around up there. So if you want to go up with Jack and capture some calories, that's your opportunity.
Yeah. If you want to capture, you can expend some calories. As for the wood net up there, we cut it down. I leave it on the ground. That's UofM's property and wood. I'm not going to tell people to come up and get some fireplace wood. That is their property and their materials there. So that's something you'd have to work out with them with. But yeah, we got plenty of time to cut there. And the other thing might be on these ends here, bottom and the sides, spray paint them white. So when cars come down at night, they do see those sitting on the side. Because I've looked at that. Yeah, I can see people coming down at night from the observatory, and I can see where people might mistake the distance from and clip that. Not that they want to, but yeah, it could happen. So yeah, there's some issues we have to think of. But to be very honest with everybody, I do not know when we're going to reopen that observatory. This whole thing with COVID-19 has escalated. Universities as you know, has some restrictions about everybody being vaccinated and tested before they come back to school. And I'm not going to get into that because that's a project that they are standing by. And I still don't know if we can ever get Angel Hall back again. I know Charlie's been working on that, or he's trying to get some information on it. I don't know. I really, to be honest, I was looking at Fred Adams' talk in November, and that would be nice to go back to an auditorium style to do that talk. But I kind of have my doubts that that's going to happen. So
actually, as you were saying that, Jack, I was writing myself a reminder to try to contact. I can't say her name. It's one brain dead.
Shannon?
Yeah, Shannon again, because I did email her, and I just realized that's been well over a week now, and I haven't heard anything. And that's not like her. So, and that was about the same time I was having some weird email things. Maybe it never got to her. So I'll try again over the weekend.
Yeah, I'm looking at this whole thing with, you know, their issue of reopening buildings if everybody's vaccinated and wearing a mask. I don't know if they reopen the auditorium for us. They may expect the same requirements of us, everybody being vaccinated and wearing a mask. And there would have to be some type of verification for that. So I don't know.
Responsible.
Leave that up to UofM. Yep. As for the observatory, telescope is doing well. Doing minor little maintenance repairs on some of the roof and stuff like that. But you know, it's ready to go. We could go in there, you know, if we had an open house, we could go back and use it. So I'm still open to that, but like I said, I'm still going to have to go with those guidelines from UofM. We're on their property. Any other issues or questions about that? Well, if there's no more, then I'm going to turn it back over to Charlie, and I'm going to get rid of the shared screen here. I'll have to do this right.
We can fix that. There we go.
Okay, thank you, Jack.
You off? Okay,
and,
thank you.
Recently, we received another fine issue of our newsletter from Amy, so I will turn it over to her.
I have nothing to report today.
Okay, thank you much.
Okay.
And that leaves us with Jeff.
Yeah, he's finally here. We had a max of 27 attendees on the Zoom meeting. Interestingly, only one person on the YouTube, and they were kind of late in the meeting. We skipped our rescheduled communications committee meeting for September because, frankly, everybody forgot about it. We are rescheduled for October 13th, which I think is the Wednesday or so before the next general meeting. One of the topics we're going to be talking about is some outreach. There was an article in Scio and Telescope that it had a lot of interesting things in it, plus some possible funding sources that would be worthwhile talking. And then, of course, in lieu of things opening up at the university for whatever reason or whatever conditions, how a hybrid or a broadcast meeting would go, because maybe not everybody would want to come into town or go through the COVID nonsense. So we may end up broadcasting from that whatever room they give us. So some discussions can be paid toward that. On the web front end, we've got some information, but nobody's really had time to act on it. I think beginning of classes kind of hit some of our folks pretty hard. So that's about it. Astronomy at the Beach is Friday and Saturday. Ani is going to start his H-alpha solar stuff at 3, and everything else starts at 6 p.m. And the URL that's in the chat, which I can put on there again, that's the URL with all the schedule and information. Ta-da!
Thank you, Jeff.
Mm-hmm.
Jim, did you want to remind anybody about the Tom Reichel sale tomorrow?
Yeah, Tom Reichel's equipment. Tom died late last year, and his brother is organizing an estate, and we're having a sale of his equipment in Rochester Hills, noon to 6 tomorrow and Sunday. The address is 553 Mallard Street. It's in the Avon Lakes, or I think that's the name of it, Motorhome Park. And it's between North Adams and Crooks Road off of Avon. And those of you who have reserved items, you should try to pick them up between 9 and noon tomorrow. Otherwise, whoever shows up may take it out from under you, because the object of the sale is to sell stuff. There's still quite a bit of things that haven't been spoken for, and both big and small. And Tom took care of his gear, so whatever you might be in the market for, there's 10-inch Dobbs. There's a couple of Bino viewers. One's a Denkmeyer. There are several Binocular Telescopes, Maya Uchis. These were state-of-the-art when Tom bought them about 15 years ago. And I've looked through the 100-millimeter Binocular Telescope, and it is fabulous. Of course, your pockets have to be a little deeper than mine, but like I said, there are other things. There's tripods. He had more tripods than I can imagine anybody ever having until I saw all these tripods. There's a lot of them. So if you need one, and they're all there's a couple that are dogs, but for the most part, they are in good shape and very useful. Lots of eyepieces. So hope to see a bunch of you there. It's a long haul from Ann Arbor. It's over an hour drive, so there's nothing we can do about that, but it's a chance to pick up something you might have wanted for a long time, but didn't think you could afford. Well, point of the sale is to sell this stuff, so you can only show up and see what kind of deal you can make.
Jim, what methods of payment are going to be accepted?
Cash or money orders, but yeah, bring exact change if you can. The catalog went out to everybody. The email with the link you should have gotten that so that you can go through the list. Not everything is in the catalog, just almost everything. But most all the things that most people would want are in that catalog. There are some carry bags, like tripod bags and telescope bags, that didn't make it to the catalog. But otherwise, it's fairly complete. And again, any questions?
Just real quick, didn't you say in the email you would take checks also?
No.
Okay. Well, I'm glad I found that out.
Yep. No, Charlie, you gotta bring cash.
Fortunately, I keep some cash stashed away. So.
Yeah, hit the ATM.
Got it.
Maybe a valid question, is there any like electronic transfer like PayPal or Venmo or those kinds of things? Or are they cash or money order?
Robert didn't want to deal with it.
Okay.
Robert, Tom's brother, is the executor.
That's fair.
And I'm pretty convinced that a lot of this stuff has to be sold through Astomart or Cloudy Nights, but he hasn't been wanting to do that either because shipping is a real big pain in the butt. So, I'm for the members, those of you that are still here, if you see something, let me know, and we'll figure out a way for you to get it. But for the greater, wider world that has gotten the catalog, they have to show up.
Jim, can you send out the link to the catalog again?
I'll do that. I'll send it via email. These are all things that are buried in my very disorganized email account. So, but I'll find it and I'll send it to you.
Okay, I'm looking for a reticle eyepiece. So.
I don't remember seeing anything like that.
Yeah, I don't think there was. Okay. Does anybody have anything else? Well, then, do I hear a motion to adjourn? I see two hands. 3. Okay, adjourn. Thank you, everybody. Have a good evening.
All right.
Good night.
Good night.
Good night, all.
Good night.
See you, Jim.
Good night,
Yep, see you in
people
the
of Earth.
morning.
Yep, I'll see you in the morning.
Can't spell adjourn. That doesn't look right either. I'm gonna send out more photos of that H alpha thing. That was just too much fun this afternoon.